This video is about molecular polarity, and we will talk about polar bonds and polar molecules. Now, when we were looking at general bonding theories, we saw that we have different type of bonds, and the main bonds that we were looking at are covalent bonds and ionic bonds. So covalent bonds are between nonmetals, and if you have two atoms that are identically the same, they will share the electrons equally. And you can see that that is pure covalent bond. On the other end, you can have an ionic bond where electrons are transferred from one metal to a non-metal. And the atoms are held together by the attraction between the two charges. There is in between a situation where electrons are shared unequally between two atoms. When does this happen? When the bond is formed by two different atoms like hydrogen and fluorine. Now remains the idea of trying and determine which bonds are polar and which one are non-polar within the covalent bonds. A measure to establish that is given by electronegativity, which we've seen as the tendency of an atom to attract electrons toward itself. Now, this can also be used as a measure for atoms to actually form polar bonds or non-polar bonds. Now, just as a reminder, I put there the trend of the electronegativity. Now you can see that besides having a trend, you do have specific numbers associated with electronegativity. Now, a polar covalent bond is formed when we have two atoms that are bonded together that have different values of electronegativity, and this will cause the electrons to spend more time around one of the atoms, the one that is more electronegative than the other. So you can see in this representation that the red is where you have more like negative charge, and the blue is where you have less negative charge. Now you do represent that not with full charges, simply because you don't have a separation of charges, you just have a shift in the electron cloud. That's why we used partial charges, which are indicated by the Greek letter delta. So you see the delta negative and delta plus to represent that. Now, the difference between electronegativities can be represented by a dipole moment, which has different magnitudes. And you can see here that you have two opposite charges, they're placed at a certain distance, and the dipole moment is going to be the charge multiplied by the distance. And you have a direction that goes from the positive to the negative charge. Now, depending on how big the dipole moment is, so the difference in electronegativity, you can distinguish among different type of bonds. So this is the same type of bonds we've seen so far, but seen from a numerical point of view in terms of electronegativity difference. So you see if the difference in electronegativity is larger than 2, that always happens when you bond together metals and nonmetals, then you have an ionic bond. Now, if the difference is between 0.5 and 2, then you are in the non-metal kind of area. And so you have covalent bonds. Now, if the difference is less than 0.5, your bond is still non-polar because the dipole moment is not big enough to make that bond polar. We don't really need to know all the numbers, so I'm going to go back for a moment to that electronegativity table, and you see the numbers. The ones that you want to keep in mind are the exceptions. So you see the hydrogen is 2.1 and the carbon is 2.5. Carbon-hydrogen is a very important non-polar bond, so we definitely want to remember that. We do have other non-polar bonds. So if we look between sulfur and bromine, for example, we would have a 0.3, but we're not going to focus our attention on remembering all those numbers. But the carbon-hydrogen one is one you want to keep in mind. It's very important, especially in organic chemistry when you're dealing with a lot of carbon-hydrogen type of bonds, and you want to make sure that you know that those are non-polar. Now, if you have a polar bond, then your molecule that contains the polar bond may be polar. And we're going to see that in more detail. If a molecule does not contain a polar bond, the molecule is definitely non-polar. So when we're looking at our CH4 methane, it only has carbon-hydrogen bonds. Now that molecule is for sure non-polar because it doesn't have any polar bond. Now, why is polarity of molecules so important? Polarity affects a lot of properties, physical properties. So, for example, you know that water and oil don't mix, and that is based on polarity because water is a polar molecule, oil is a non-polar molecule, and in general, the rule is that polar molecule will not dissolve non-polar molecule. So the rule is known as like dissolves like. Now, how do we determine if a molecule is polar? So we say step number one, is there a polar bond? Because if there isn't one, then the molecule is definitely non-polar. So if we have a polar bond, then if the dipole moment is large enough, and we refer to that table with the values less than 0.5 is non-polar, but if it's large enough, then you have a polar bond. Now, if your molecule has a polar bond, and is, for example, a diatomic molecule, then that molecule will be polar. So for diatomic molecules, it's very easy. If it's a polar bond, that molecule is polar. So HCl, you can see there the difference in electronegativity is larger than 0.5, so that molecule is polar. Important, polar molecules are neutral. They have those partial charges. They don't have full charges, so they're not charged molecules. They're not like polyatomic ions, very different. Now, what we if we have a molecule that is polyatomic, so we have more than two atoms there. Now, you have to evaluate the polarity of all the bonds there, but also the geometry of the molecule. So you see how the Lewis structures and the BS-EPR theory come into play into this. So what we can do is draw the Lewis structure for a molecule and then look at the dipole moments and then sum them up because they're vectors. And then we can determine if the sum of the dipole moment is more than 0, so it's non-zero, then your molecule is polar. Now, there are simpler ways to do this that is not by summing up electrons. So let's look at some examples on how to do this. So if you have a molecule where you have no lone pairs on the central atom, and all the atoms bonded to the central atoms are identical, so carbon dioxide, you can see that the dipole moment, the sum of the dipole moment of each bond is 0. So this molecule is non-polar. Now, this is going to be true every time we have a molecule of this kind. So any molecule that has all the bonded atoms to the central atom identical and does not have lone pairs. So we can see that this applies to all these geometries. So all these geometries will lead to having a nonpolar molecule if all those bonded atoms, you see they're all purple to indicate they're all the same. So in general, you do not need to do the sum of the vectors. You can just look at the geometry and determine whether the molecule is nonpolar. So say, for example, boron 3 fluoride, BF is a polar bond, but we have a trigonal planar geometry. All the atoms are bonded to the boron, are all fluorines, so they're all the same. There is no lone pair there, so the molecule is non-polar. What about PCl5? What if you had a question that says, determine whether PCl5 is polar? How do we solve that? Now, first of all, we need to determine if that bond is polar or not. As it turns out, the value of the electronegativity for P is 2.2, for fluorine is 4, so those bonds are all polar. The next thing we need to do is draw the Lewis structure. So you can see the Lewis structure there. Now you have, as I say, two ways to do this. So you can sum the dipole moments, or more simply, you look at the fact that all the bonded atoms are the same. You have no lone pair on the central atom, hence this molecule is non-polar. Now, what if you have a case where you have a lone pair on the central atom, so say ammonia. Now you can see that if you have a lone pair, your geometry is different than what we were looking at before. So this will create an asymmetry in the molecule, which means that the dipole moments will not sum up to 0. So NH3 is polar. So in general, if you have a lone pair on the central atom, your molecule is polar. You have an exception, the square planar geometry with identical bonded atoms, that is going to be non-polar, because in that case the two lone pairs are on opposite ends, and so they do cancel each other. What if you have a case where the bonded atoms are different? Then in this case also, if you have some polar bonds in there, then your molecule is going to be polar. So see the CH3Cl. Now the CH bonds are non-polar, so they don't factor in, but the CCl bond is polar, and so your molecule ends up being polar. If you have CH2Cl2, also these will be polar. So in general, every time you have different bonded atoms and you have at least one polar bond, your molecule is going to be polar. So you can see, for example, in PCl3, if you do the Lewis structure, you're going to end up with a lone pair on the phosphorus. So you have the polarity there because the three bonded atoms are the same, but you do have a lone pair. And so that will generate a polar molecule. For HCO, you can H2CO, you can look at that. The atoms bonded there are different, and so this molecule is polar as well. So these are your two cases. So in general, if you want to look at an example, you can look at the table like this, and this is what you're going to do with the next Lewis lab. So say, for example, you want to determine if a molecule is polar, so you can get your NH3. So I'm going to do the case of NH3. You're going to say, okay, I need to do the Lewis structure first. So that's my starting point. Once I have my Lewis structure, I'm going to say, okay, do I have polar bonds? So I can look at the values here, and I can see that between nitrogen and hydrogen, I do have a 0.9. So these bonds are polar. And because I have polar bonds and I have a lone pair, so the bonded things are not the same, so this molecule is polar. If I have something like CH4, so that was my other example. I'm going to slide this up. So CH4, Lewis structure first. Now I look at this molecule and say, okay, I do not have any polar bond here because carbon 2.5, hydrogen 2.1, 0.4, so this is non-polar.